Each of these tiny uranium fuel pellets releases enough thermal energy to produce 1 million kilowatt-hours of electricity, enough to power thousands of homes for an entire year. But have you ever stopped to wonder how enriched uranium is actually made? How can something the size of a peanut hold that much power? Today, we're going to uncover how uranium is pulled from deep within the Earth, and how one of the most dangerous materials on the planet is transformed into clean energy. Stay with me until the end, because this journey into the heart of nuclear energy will completely change the way you look at the tiny pellet powering your world. The story of enriched uranium is deeply connected to the history of modern science. Uranium was first identified as a chemical element in 1789 by German chemist Martin Heinrich Klaproth, at a time when no one imagined the energy hidden inside it. It wasn't until 1896 that French physicist Henri Becquerel discovered radioactivity after observing that uranium spontaneously emitted radiation. This breakthrough inspired Marie and Pierre Curie to discover other radioactive elements, including radium and polonium. In 1932, James Chadwick discovered the neutron, the particle that would later make nuclear fission possible. Just a few years later, in 1938, German chemists Otto Hahn and Fritz Strassmann demonstrated that uranium-235, a rare isotope in natural uranium, could be split when struck by neutrons, releasing enormous amounts of energy. Natural uranium is made up of about 99.3% uranium-238, which does not easily undergo fission, and only 0.7% uranium-235, the isotope capable of sustaining a chain reaction. The process of increasing this percentage is called enrichment. During World War II, the United States brought together the greatest scientific minds under the Manhattan Project, led by figures such as Enrico Fermi and Robert Oppenheimer. They developed enrichment, methods such as gaseous diffusion and high-speed centrifuges, to separate uranium isotopes based on their slight differences in mass, the most dramatic outcome. Of this effort was the atomic bomb dropped on Hiroshima in 1945, which used highly enriched uranium-235. After the war, attention shifted toward peaceful applications of nuclear energy. For nuclear power plants, uranium only needs to be enriched to about 3 to 5% uranium-235. Weapons-grade uranium, however, requires over 90% enrichment. Today, nuclear energy provides around 10% of the world's electricity. Everything begins underground. Countries like Australia, Kazakhstan, and Canada supply most of the world's uranium. It is found in a mineral called uraninite, usually at very low concentrations. But in Saskatchewan, Canada, some of the richest uranium deposits on Earth are found, with ore concentrations far higher than the global average. The challenge is that these deposits lie beneath thick layers of sandstone filled with groundwater. To safely extract the uranium, engineers use a method called artificial ground freezing. Special pipes circulate supercooled liquid that freezes the surrounding water in the rock, creating a solid barrier that prevents flooding and stabilizes the mine. Once the ground is frozen, drilling begins. Ore is broken apart using controlled techniques and brought to the surface using remote systems to protect workers from radiation and collapse risks. The ore is then crushed into a fine slurry and transported to a processing plant. At the mill, uranium is chemically separated from the rock using acid, purified through multiple stages, and then converted into uranium hexafluoride gas. This gas is fed into high-speed centrifuges, where the slight weight difference between isotopes causes uranium-235 to separate and concentrate. The result is enriched uranium in powder form, packed into sealed steel containers and shipped to fuel fabrication facilities. At these facilities, the uranium is converted into uranium dioxide powder and pressed under extreme pressure into small ceramic pellets, each about the size of a peanut. A single pellet contains energy equivalent to thousands of kilograms of coal or hundreds of gallons of oil. The pellets are then sintered at extremely high temperatures to increase density and strength. After this, robotic systems load the pellets into zirconium tubes, forming fuel rods. These rods are assembled into fuel bundles that will be used inside nuclear reactors. Inside the reactor core, uranium atoms split in a controlled chain reaction, releasing enormous amounts of heat. This heat is used to turn water into steam, which drives massive turbines connected to generators. These generators produce electricity on a massive scale, enough to power hundreds of thousands of homes from a single reactor. After about a year of use, the fuel becomes spent, but it remains highly radioactive. It is transferred into deep cooling pools, where it must remain for many years before it can be safely managed. Today, hundreds of thousands of spent fuel rods are stored in facilities around the world. And yet, this entire chain, from rock deep underground to electricity in your home, comes from something small enough to hold in your hand. This is the hidden power of nuclear energy,